Good day. Welcome back to the online course on groundwater quality, where we are looking at groundwater quality in transboundary aquifers. This is still part of Module 2, and I'm Dr. Israel from UWC in Cape Town, South Africa. In this part of the module, we will be looking at mapping and modeling of groundwater quality. Some of the learning outcomes for this section: we will be looking at selecting and defining assessment areas and identification of quality issues and potential pollutants. We may have touched to some extent on potential pollutants in some of the previous videos. When we think about mapping and modeling of groundwater quality, we need to take into consideration that chemical reactions are taking place from the moment that rainfall hits your surface rocks, during the infiltration or percolation process, along the flow path, as well as in the discharge zone. This emphasizes the importance of visualizing your study area, if it's a regional or relatively large, where you've included the recharge and discharge zones. You would need to spatially visualize the entire area to account for those chemical reactions that may be taking place. Why do we map it? There are several factors that influence the concentrations that we see in our when we collect data, and these factors occur along the flow path, and they vary spatially, and some vary temporally as well. By mapping, we get to visualize these spatial and temporal changes. Some of the factors refer to your aquifer properties, and some of them to your flow, recharge, and discharge processes. Also, the type of aquifer that you have. So these three interact to give you a resultant hydrogeochemistry. The time that your water is in contact with your lithologies, the type of aquifer unit that you have, and the amount of recharge that you receive, all of those play a role in what you see when you analyze a sample. So there are several tools that one can use to do mapping, and these include various GIS-based tools, some programs like Surfer, and then you can even visualize using Google Earth images. You would need to have spatial data, so georeference data or point data with coordinates that you're able to plot in these software packages. And of course, values or data for the respective parameters that you want to visualize. If you wish to look at time series or time plots, for example, you want to visualize or you want to see how a particular parameter changed between two different time periods, you would need temporal data for that parameter in order to do that. These are two examples of students that have just finished their master's studies. On the left, you see groundwater level contours with flow direction indicated. On the right, you see oxygen 18 data. So these were done in GIS software. And as you can see, they've categorized the data, and on the left, they've used contouring, and on the right, they are showing circles with different colors to represent the different classes. These are simple examples. They are much more complex things that you can do. As an example, vulnerability mapping. One of the most commonly used vulnerability mapping methods is drastic. And the parameters that are considered there includes the depth to groundwater table, the net recharge, your aquifer media, your soil media, your topography, and impacts of your Vado zone, as well as hydraulic conductivity. If you look on the left, you can see that these are applied as layers in your software, and you get a resultant groundwater vulnerability map. So each of these parameters would have their own ranges of values that can occur. Your rainfall amount and intensity normally influences your vulnerability. Similarly, the properties of chemical species that may be present, for example, volatility, solubility, distribution coefficients, and sorptive capacity, these would influence how and whether your chemical would be moving in your groundwater. Each variable has a different range of properties, as I've mentioned before. As an example, different geological units would have different intrinsic properties, and that contributes to different vulnerability ratings for that particular parameter. So this type of mapping is a method or a way that you can combine the physical properties with the properties of contaminants where contamination is present. You would be able to predict areas of high vulnerability and areas of low vulnerability in a particular study area. The map in the middle shows different vulnerabilities based on, on some input data that has been used. So when we look at contamination, it's good to have some kind of understanding of history and up to present day inputs. So if you look at development, things like industry, urbanization, and agriculture, these have changed dramatically over, say, the last 10,000 years. And these influence the type of contamination or the type of parameters that we have to be looking for in our groundwater streams. As you can see, if we look at industry, for example, we talk about the early mines of lead, copper, and silver started more than 1,000 years ago. And if you follow the industry section, you'd find that chlorofluorocarbons only came into our atmosphere or into existence in the last 100 years or so. If we look at agriculture, we can see that the first farming started really long ago. And at that point, there were very little synthetic pesticides, which we now find in our water systems. When we consider pathways of contamination sources, we need to take into consideration, of course, our rainfall amount, like we've briefly discussed in the vulnerability mapping. But so there are many sources that sit on the surface that comes into contact with our rainfall or sit in basin type structures and or are in contact with our surface water bodies. And these are all able to get into our groundwater via percolation, leakage, discharge, and interaction with the different water bodies. If you look at the different types of aquifers here, we have a water table aquifer, which is unconfined. Unconfined aquifer systems are normally very vulnerable. Then we have a confining zone. This would serve as a protection because it's an impermeable layer, which means to some extent, whatever enters into our water table aquifer might not go beyond that confining zone. When we have boreholes that penetrate through our confining layers, this might be a conduit for some of the pollutants to possibly leak into other areas. So we've seen how the contaminants can enter into our groundwater and surface water systems. We then go further to look at risk assessment, so the pathways in which those contaminants can then reach us again. So one would be through atmospheric pathways, there would be surface water pathways. The other would be through the biosphere, plants and animals, where we might eat some of these, and that's how it would enter our bodies. And so also from inhalation of some gases that might emanate from some pollutants. So the other important aspect that we need to take into account is how do contaminants move? So how are they transported? And there are a few mechanisms. Advection, which is that contaminant moving at the same rate at which your groundwater is moving. So that is typically adhering to Darcy's law. Then we have diffusion. This is independent of the rate at which your groundwater is moving. This type of movement is very important when we look at areas that contain aquicludes or clay layers. It's also very important for fractured rocks. Then we have advection dispersion, which is a combination of movement at the flow rate as well as hydrodynamic dispersion. Retardation, here we are talking about those parameters or those chemical compounds that are likely to sorbed onto your soil surfaces. These are likely to slow down the movement if it's part of a plume. And you'll find that the concentrations will reduce over time. If we compare a contaminant moving by retardation or that undergoes retardation with advection from point A to point B, the one moving by advection will arrive at point B first. The retarded one will arrive there eventually, but the concentration will be considerably reduced. In conclusion, it's important to display data spatially and to understand the temporal variations in your concentrations. This aids in understanding the distribution of specific chemical species, and also it aids you in explaining processes like recharge, for example, discharge. You can also gauge the age of groundwater by looking at isotopes at various locations, and also the flow path or flow characteristics. Contamination sources and pathways are very important in terms of setting up monitoring programs or monitoring networks. You would need to know their sources and their pathways in order to, for example, select a location to take a sample and to understand if there's any plumes, how they move. I think that's it for this presentation. I hope you've taken some valuable information from there. Thank you.